Okay, so today we discuss systems with random processes input. Suppose x t is a random process. That means you conduct experiment, and with every time you have an experiment, you know you observe one waveform, right. So, maybe one particular waveform we denote as before like this, where S I denotes the ith outcome. Okay. So, in the ith outcome you get a waveform as a function of time. So, this is represented by x t comma S I. So, it is actually a function of time. S I just denotes the fact, S I just stands for the fact that it is related to the ith outcome, a particular waveform. Now, suppose we have some kind of rule, we develop or we have some kind of rule by which given particular waveform we generate another waveform by a rule, some waveform we call it y, and obviously that waveform also is associated with the ith outcome of the experiment. Okay. So, that means we can write it as y t s I. For example, you can you can have a very simple rule, it is nothing but say twice x t s I say plus 3, which means whenever you observe a waveform, say for the ith outcome you have a particular waveform, this is x t comma s I. Now, take that waveform, multiply by 2, add 3 to at each t, whatever waveform you get, that is what in this case is y t comma s I. So, that means for the same outcome s I, we have a waveform for x and we then have a waveform for y. So, that means we can say that we have generated a random process y t whose waveform for the s ith outcome is given by y t comma s I. In other words, given x t, we say that we generate a random process as t working on x t, where t stands for operator, or that is the rule or the way of mapping. The given a waveform x t comma s I, we mapped it to another waveform by some rule. So, that mapping or that rule that is contained in this operator t. So, t takes each waveform of this random process x t and maps it to another waveform y t. Okay. So, thereby we generate a random process y t. Obviously, because with each outcome I am not only getting now a waveform for x t, I am also getting a waveform for y t. Okay. And therefore, you can also say that y t is such a random process whose waveform for the s ith outcome is y t comma s I. Okay. So, I repeat again, we have this. So, this t, which is actually a rule by which you map each waveform of x t into a waveform of y t, this rule actually in a bigger sense is called system. So, t stands for the system operator or the mapping rule, but we normally prefer to use the term system. So, that means the system takes x t and maps it to some waveform, okay, of y t. Now, if it so happens that given this waveform x t comma s I, when t works on it, if capital T, that the system works only on this as a function of time and takes s I as parameter, then we say it is a deterministic system. That is, suppose S I and S j are two different outcomes, but the waveforms are same. It so happens the two waveforms are same. In that case, if these two are same implies t of x t comma s I should be same as t x t s j. That is, the system only looks at the time t, it does not look at the experimental outcome, it does not look at the s value. So, whether this time you observe a waveform or after some time for another outcome you observe the same waveform, in both cases your output will be same. because the system only looks at the function as a function of time. Okay. It does not look at the particular experimental outcome with which it is associated. If that be so, then it is called deterministic system. But if it so happens that a system not only treats this as a function of time, but also looks at the particular experimental outcome, that is, even if after getting this waveform x t comma s I, for another outcome x s j, you have the same waveform. Suppose if the system acts on that waveform differently, that is, it not all it changes its behavior from outcome to outcome, then the system, that is, now system is changing its property with time from outcome to outcome. So, in that case the system is called stochastic system. Okay. If that is suppose it is given that is for two outcomes S I and S j, the two waveforms turn out to be same. But if the system is stochastic, it will not give the same output, because it is not only looking at these waveforms just as function of time, it is also considering the particular outcome. So, for our outcome S I, its behavior will be different from its action when the outcome is S j. So, in general T of not equal to in general, this leads to T as stochastic system. That is, if T is such a system whose individual parameters, built-in parameters or into internal parameters, they vary randomly, that is, they vary, they undergo change from experimental outcome to outcome. Obviously, the action of the system will also change. In that case, the system is stochastic. So, its behavior on this x t comma s I and x t comma s j, even if the waveforms are same, will be different, because with change in experimental outcome, system parameters have changed, so system behavior has changed. But in this course, we will be considering mostly systems that are deterministic, not stochastic. Okay. A particular case of deterministic system is what is called memoryless system. That is, suppose given a function y equal to g x, that is, give any value for x, we find out y. This memoryless system will be given by y t as g of x t, that is x t, that is, for each experimental outcome you have got some waveform for x t. What g does, at each t it takes the value and evaluates this function g of x, that is g of that value, and gives you the corresponding y. So, obviously, here when g works on that value, it does not look at the past or future of x t. As a result, we call it memoryless system. Okay. I repeat again, what it does, we know this function that given by any value of x, how to work out g x and what is y, that we know. Then this system is constructed like this, that this random process x t is the input, g work on it and give you y t. Its meaning is, take any experimental outcome, say x t comma is I, that is the ith outcome. There for each, so you get a waveform. In that waveform, for each time t, you have a value for the waveform, that is amplitude or whatever. Okay. G works on that as per this given function and gives you a value. That value is assigned to y t. So, here as you see, it will work on the instantaneous value of this waveform at a particular time. It will neither look at future, not look at past. So, this will be called memoryless system. A memoryless system, if the system is memoryless, then if the input is stationary, if it is a strict state stationary SSS, then output also SSS, that we can see. Just let me write down first. Okay, we will prove it. First, this is y t. You find out time t 1, t 2 dot 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 say t n. You will find the joint statistics, the joint probability density or distribution, anyone will do, okay, for the samples of y at these values t 1, t 2, and then if that joint density does not undergo any change, if a constant shift is given to all these time points, that is instead of t 1 I go to t 1 plus c, t 2 plus c, t n plus c, if we still get the same joint probability statistics, then by the definition it is fixed and stationary. We will check, suppose it is given that input is fixed and stationary, that is x t, if you take a waveform, given x t, given x t is S S S. Now, remember we did some study on this, joint statistics of a group of random variables, and that is given the joint density for x, that is x t 1, x t 2 dot 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 up to x t n. If I take those variables and if I take those random variables, take the joint density, how to obtain the joint density for y, okay, that is how to obtain the joint density for y t 1, y t 2 and y t n dot 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 y t n. So, there is a formula that involved the joint density for x, that is x t 1, x t 2 up to x t n, and a Jacobian. What was the Jacobian? Jacobian was in this, the Jacobian you remember, in this case for the Jacobian will turn out to be this excuse me, is this first this y t 1, it is a function of just x t 1, it is not a function of the other variable x t 2, x t 3, x t n, that is y t 1 okay. Obviously, del y, if you call y t 1, if you denote y t 1 as y 1 and x t 1 as x 1, this is d x 1. Okay. Obviously, del y 1 del x 1 is g prime x 1, but del y 1 del x 2 is 0 dot 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 del y 1 del x n is 0. What is x 2? X 2 is x t 2. What is x n? That is x of t n. It is a short notation. Similarly, when you consider y at t 2 and call it y 2, then del y 2 del x 1, that is 0, because y 2, that is y t 2 is just g of x t 2, that is g of x 2. Okay. So, you see that Jacobian becomes a diagonal matrix, g prime x 1, g prime x 2 dot 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 g prime x n, and 0 here, 0 here, and that expression involved the determinant of this matrix. So, determinant is obviously product of this mod of determinant. So, mod of this product of these diagonal entries. So, if you do that, what happens to the joint density, that is this y stands for the fact that I am looking at the joint density for the y variables at say y 1, y 2 dot 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 y n at what values t 1, t 2 dot 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 t n, that will be p x by that formula divided by the Jacobian expression, and Jacobian you have seen, it will be mod of g prime x 1, g prime x 2 dot 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 g prime x n. Okay. Now, we are given the fact that input is fixed and stationary. So, you see, is it true for output? For that, if I give a constant shift, if t 1 is changed to say t 1 plus c, t 2 is changed to say t 2 plus c, t n is changed to say t n plus c, Then here also by this formula T1 should be changed to T1 plus C, T2 should be changed to T2 plus C, Tn should be changed to Tn plus C. But since input is strict and stationary, this will not produce any change. I will get the, because the shift is constant, because of strict and stationarity I will get the same expression. So, it does not make any change here, and you see the denominator is independent of time. So, it does not get changed by this shift in t. So, that means there is no change in the LHS expression. So, whether you keep T1, T2 up to Tn or give each of the values a constant shift by C, which obviously means that output also is strict and stationary, and if strict and stationary it is WSS also. Okay. We now consider a particular case of systems called linear systems, which is not necessarily memoryless system, this linear system. There is another important system, linear systems. Here we use the notation L to denote for that, stand for that operator system, okay, because L stands for linearity. System is linear if suppose you give one waveform for a particular outcome x, suppose x t s I, L of that is some waveform y t s I, again x t s j, another waveform y t s j. Now, suppose you have an experimental outcome where the waveform is actually a linear combination of these two waveforms. That is, suppose you have got a situation where x t s k is nothing but a linear combination of these waveforms. Whatever you had for these, C 1 times that plus C 2 times x t s j. Now, if it is linear, then L working on this guy, it would generate obviously y t comma x k, the waveform for y for the same outcome x k. If it is linear, if this becomes same as the response C 1 times the response due to this first waveform, that is x t comma s I, plus C 2 times the response due to the second waveform x t comma s j. That is, if it turns out to be C 1 times y t comma s I, this particular waveform, plus C 2 times x t comma s j, which means principle of superposition should be valid. That is, if you have one waveform x t comma s I, you get y t comma s I. Similarly, another waveform x t comma s j, get y t comma s j. Now, if you linearly combine them as C 1 x t comma s I plus C 2 x t comma j, two waveforms are linearly combined, the corresponding response should be simply C 1 times the response due to x t comma s I, that is y t comma s I, plus C 2 times the response due to x t comma s j, that is C 2 times y t comma s j. So, the principle of superposition should be valid. If that we show, then it is called a linear system. Okay. A particular class of linear system is linear time invariant system. I will come to that later, but before that let us do some let us recall something from system theory. That is how to describe a continuous a linear continuous time system. Okay. Now, you all are familiar with this thing, this Dirac delta function or unit impulse function delta. What is delta? Delta t is such that is 0 if t not equal to 0, and integral of delta t dt, all of this is Dirac delta function or unit impulse function. You all know this, that you start with a box function whose area is 1, start compressing the box, but keeping the area 1. So, the height increases. Okay. Finally, in the limiting case it becomes that impulse, area remains same as 1, but since outside origin it is 0, at origin it is shooting up to infinity, that kind of function. Okay. Then, since it is not a class on system theory, I cannot go into those details, but any waveform, any function say x t For the time being, for convenience, I am dropping this second parameter, that is, earlier I was writing x t comma s I or x t comma s j. For the time being, I will just write it as x t, meaning a waveform, that is a function of t. But actually, since they are coming from random process, I should also mention s I or s j, indicating the particular outcome with which this waveform is associated. Okay. But for the time being, just for convenience, I am dropping that notation, I will be dropping that symbol. So, now given any x t, this is there in system theory, you can verify also, you can write it as this. Okay. You obviously get x t, because again this delta, if is delta t minus tau is the impulse shifted at tau, that is, you are doing an approximation of the impulse first by taking a new box of area 1, you have shifted it to tau, earlier it was centered at origin, and now you start compressing it here, and finally, in the limiting case it becomes an impulse at tau. Now, what is happening is, you are not only taking the box, multiplying the box by a value x tau. So, area is not 1, but x tau, and now start compressing it. Okay, so, area will still remain x tau. Okay. Actually, you are multiplying with, sorry, you are multiplying, first you are approximating delta t minus tau by just a box of area 1, and there is a function x tau, this axis is tau. Okay. You are multiplying it by tau, you have shifted it to t actually, because all these are function of tau, t is constant, t is your choice from outside. So, t is fixed. So, there is a box approximating the delta as a function of tau, its center is t. Remember, delta t minus tau or delta tau minus t, they are same. Okay. Delta t is such a function, whether you replace t by minus t or keep t, it does not make any change. So, actually delta t minus tau means delta tau shifted by t. So, center is at t, you are multiplying it by x tau. When you multiply the two, okay, then only in this area only where the box is located you get a multiplication, otherwise everywhere else this function x tau is multiplied by 0. Now, you start compressing the box keeping the area 1. Okay. So, in the limiting case what happens is this, you get a value x t, because if the box is sufficiently narrow, then what is the area of the box? Not just 1, but multiplied by the value of the function. Now, if the box is sufficiently narrow, that function is infinitesimally small width, then that function has actually approximately value equal to x t, that is the value at the center point, that is at t. The x t times the box area, that is x t. You still compress it further, so area will be, you will get finally and you are integrating. So, you get actually x t. Okay, details are given in system theory book. This is just to kind of recap, so that we do not get terribly confused. Now, if such a system is passed through a linear system, what happens? In general, delta t, that is an impulse at origin, we denote it by this delta t. If delta t is passed through a linear system, output is called the impulse response H t as del L of delta t. If instead of delta t I give delta t minus tau, this is a more general case. So, in the general case, the output here will depend on what? The two indices. Usually function of t, I agree, but it will also depend on that shift parameter tau by which the delta has been shifted. If the system is shift invariant or time invariant, then it should only depend, it should not depend on, it should only depend, I mean the waveform that you get here will be same as h t, just h t will be delayed by the same amount tau. That is, without any shift or without any delay in delta t, you got h t. Now, you delayed delta t by some tau. So, corresponding response also should be h t minus tau, that is previous response delayed by the same amount. But in general, that happens when the system is time invariant. That is, there is a gap of tau in giving the input delta t. That is why I am giving now input delta t minus tau. Within that time period tau, the system has not changed its property, system is time invariant, and therefore, the response now also will be in nature same as the previous response h t, but if you plot it on the same scale, it is now again delayed by the same amount tau. So, on the same scale if you plot it, it will be not h t, but h t minus tau. That happens in the time invariant case, but in the more general case, system may change its property within that period tau. So, output for delta t minus tau will not only will depend on two things, it will be a function of t, but it will also be a function of tau. If instead of tau you delay the impulse further by say tau prime, the corresponding impulse response might be different, because system is undergoing change in property with time. Okay. That is why in the general case it is a function of two things, h t comma tau. Only when it is time invariant, it is not h t comma tau, but it is just t minus tau. There is same h t delayed by the same amount tau, because input is delayed by the same amount. But in general, if it is not system time invariant, that is if its property also changes with time, then impulse response as a function of time should also depend on by how much this parameter tau by which the input is shifted. If it is shifted further, maybe I will get some other kind of waveform. Okay, not only just the delayed version of h t, but even the nature will change. So, let us take this. See this case y t we have already expressed x t in terms of like this in the previous slide, and L now it is a superposition because of integral, and system is linear. Integral only means summation, but if the system is linear, superposition principle works. So, if you apply the system after the summation, you should get the same thing. If you apply the system before, that is L over this integral is same as integral over L working on these inputs. Okay, you remember system response over a summed input is same as sum of the individual input in responses. That is, because of linearity, you should have L working on this. Integral is only a summation. That is individual responses summed. Earlier, I was taking the response up by first summing the various inputs by the integral, then applied to the input. Because of linearity, that would be same as first applying individual inputs x tau times delta t minus tau, getting the corresponding response, and then summing the individual responses by an integral. And remember, here is a function of time, only delta x tau is kind of amplitude. So, L will work only on this. So, this is x tau, and I know L working on delta t minus tau. As I said earlier, it will be function of two variables in the general case h t comma tau. Remember this result. Okay. Now, using this result, we will prove some results, some other results. So, I rewrite again. First, if I take the mean of this mu y t at a particular time t, that is E of y t, that is E of the right hand side, but right hand side is a summation, and you remember E was E, the expectation operator is linear, that is E expected value of a sum of random variables is the same as sum of the expected value of the individual random variables. Only thing is here you have got a continuous sum in the form of integral, but still the linearity property of E operator prevails. So, that means this is same as you can push E inside the integral, and H is not random. So, E will work only on x. That is mu x tau h t comma tau d tau, and that is same as L working on this function. Okay. Remember, when L was working on any function x t, I put x tau h t comma tau d tau integral. Now, instead of x t, now I have a function mu x t. So, that is a mu x tau h t comma tau d tau. So, as though the mean function, that is if you take the mean or expected value of x, you again get a waveform. It is not a random waveform, but waveform. If you pass it through the system, whatever output you get, that is what you get for the mean waveform of the output. Okay. This is number 1 result. In the special case, when it is LTI, linear and time invariant, LTI, in that case we know that YT is not t comma tau, but it is actually really delayed version by tau. Okay. If giving delta t as input, you got h t as impulse response. Now, delta t shifted by tau, so h t also will be shifted by the same amount tau. Okay. That happens when it is not only linear, it is linear and time invariant. This is a special case. And there, if you replace t by minus tau by tau prime, so tau is t minus tau prime. Okay. And then you see d tau is minus of d tau prime, and when tau is minus infinity, tau prime is plus infinity. So, plus infinity or minus infinity here, d tau means minus d tau prime, or minus has come, you reverse the two limits again. So, minus infinity to infinity, another minus comes, so it becomes plus, and you get back x tau prime h, sorry, you get back this x t minus tau prime h tau prime d tau prime. I repeat again, if you replace t minus tau by tau prime, so d tau prime is minus d tau. So, d tau is minus d tau prime, so minus is coming. Then look at the limits, tau becoming minus infinity means tau prime plus infinity, and here minus infinity. So, plus infinity to minus infinity, reverse the limits, minus infinity to plus infinity, so another minus sign. So, two minuses cancel each other and you get back this relation. At no point in carrying out with tau prime, you can again bring back your good old tau. Okay. In such case, mu y t is what? And this is called convolution. This is called convolution between two sequences x t and h t. This is the formula. Okay. Now, in this case, what is mu y t? Mu y t is apply E, push the E inside, E works on x t minus tau, there is mu x t minus tau multiplied by h tau d tau. That is again convolution between these two functions mu x t and h t. This is the formula. Then let us find out this, that okay, there is a system, input is x t, there is a system, linear system, not necessarily time invariant, so output is y t. Okay, we know y t equal to, remember only when it was time invariant, it became a function of t minus tau, and there I could replace t minus tau by tau prime and all that. I could write it in a reverse way, that instead of writing x tau h t minus tau, I could also write h tau x t minus tau. But when it is not time invariant, I cannot proceed any further from here. So, I have to stick to this. To be most general, I still keep the linearity only, I do not bring in time invariance unless necessary. So, for the linear case, suppose you want to find out one function, one cross correlation function R x y, say t 1 t 2, that is expected value of x t 1 y t 2. What is it? Now, y t 2 we know, we put in the formula, that is x tau h t 2 minus t 2 comma tau d tau, and x t 1 multiplying that. So, we bring that x t 1 within the integral. So, x t 1 brought within the integral, y t 2 for that x tau and now expected value can be brought inside, because expected value of summation is summation of the expected values. H is deterministic. So, E will work only on this x t 1 into x t tau x tau. So, what you get is R x x t 1 comma tau h t comma tau d tau. So, that means what is it? That if you take it as a function of R x x t 1 comma tau, you just forget t 1 for the timing, take it as a function of tau, then isn't it that it is the same thing if I will get, if you give a function of tau, forget t 1, is a function of tau to the system at its input. The output obviously will be this function multiplied by h t comma tau d tau, that is what I am getting here. Just to indicate that here L means the integral will be with respect to tau, I denote tau here, I put tau here. Okay. That means, you take an integral multiply R x x t comma tau into h t comma tau integral with respect to tau. Remember, when the system works on any function, on any quantity, is a function of tau here, that is why this tau is indicated L tau, the tau is the function. Then what does the system do? You multiply this by h t comma tau, integrate with respect to tau. So, that will give you the output at t. Here it is t 1. Sorry. Okay, it will be better if I simplify it further for the LTI case, that will be better, because actually this should be y x t 1 y t 2, this will be t 2. I made a mistake, because this should be t 2, this should be t 2. So, when I say L tau means you give this input R x x t 1, in case my handwriting is not perfectly legible, I correct it again. You give this function R x x t 1 comma tau as a function of tau to the input, to the system input. The system evaluates output at a time t 2. So, that means this function should be multiplied by h t 2 comma tau integral with respect to tau, that will give you the output at t 2. That output will be a function of t 2, and also this t 1 will carry, because t 1 is given as a parameter from the beginning. So, it will be a function of t 1 comma t 2. Okay. In the special case where it is LTI, it is time invariant also. Let us see what happens. Special case LTI. In such case, I know that y t is so what is r x y t 1 comma t 2? That is E of x t 1 y t 2. So, for y t 2 put t equal to t 2 here, push this parameter x t 1 from outside the integral to inside integral, and then bring in push this E operator inside the integral again. So, what you get there is this E working on x t 1 that has come from outside the integral, then x is y t 2, it should be x t 2 minus tau, h remains separately because it is not stochastic. And what is this function? This is r x x okay. T 1 T 2 minus tau. Okay. That means you can write that this is equal to L R x x T 2, and I write T 2 here. What does it mean? This will be treated as a function of T 2 only. If just to indicate that I put T 2 here, that will be, this function is given as a function of T 2 as the input to the system. So, what is the output in the LTI case? Simply this will be replaced by T, here instead of T 2 I will have T 2 minus tau, that is what is happening here, multiplied by h tau integral. Okay. This is a cross correlation between input and output. And what is the autocorrelation in output? That is, what is your R y y t 1 t 2, this is more interesting. Here simply replace by those expressions. Y t 1 was in the, again in the just linear case, not necessarily time invariant. So, y t 1, for that we will have x tau 1 and then here x another variable tau 2 . Okay. Take the E inside the integral and on x into x, others are not stochastic. So, you get R x x here. It will be better if I take the time invariant case. If it is time invariant, then instead of special case we consider now LTI. Here so R y y T1 T2 will be what? E. Now I am doing first. Or means E y T1 into y T2. So, E of x T1 minus tau 1 x T2 minus tau 2 h tau 1 h tau 2. Okay. Okay. That is R x x what is the physical interpretation of this? Very interesting. This means what? If we just consider this inner integral R x x T 1 minus tau 1 T 2 minus tau 2 multiplied by say h T 1 h tau 1. So, that times it is a function of just tau 1. Okay. That means first you are giving this guy suppose I do this first T 1 T 2 and I say L T 1 first. What does it mean? It will give rise to an output. What output? R x x T 1 minus tau comma T 2 h tau 1 d tau 1 integral. That I will now apply here. So, again it was a function of T 2. So, now instead of T 2 it will become T 2 minus tau 2 and h tau 2 will come, again another integral. So, that means this input autocorrelation function is passed through the linear system where it first takes it as a function of T 1, then the corresponding output which is a function of T 2 is again passed through the same system. This time it takes this intermediate output as a function of T 2. Okay. A particular thing you see, if input is Weierstrass stationary, if x is WSS, then obviously R x x T 1 minus tau 1 comma T 2 minus tau 2, it will be a function of just T 1 minus T 2 minus tau 1 plus tau 2. Tau 1 and tau 2 they are integration variables. Once you carry out the integration, there will be no trace of tau 1 and tau 2. There will be, so entire thing will be a function of just T 1 minus T 2. So, that means R y y T 1 comma T 2 will be just a function of T 1 minus T 2. So, it is not individual T 1 or T 2 will matter, but the gap, which means output also will be WSS. I mean, it is in terms of correlation, in terms of mean also it will be WSS we have seen earlier. Okay. How? Because we have seen that if input is if input mean function you take mu x t, then output is mu x t convolved with h t. So, if mu x t because of stationarity is a constant thing, then that convolution will also yield a constant function. Okay. Okay. One thing does not need any proof, we just make a statement. We make a statement that if a system is linear, if L denotes an LTI system, then input SSS means output also SSS. That is not very difficult. Output, say we are trying to find out this y1, that is y of t1 dot 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 say yn comma t1 dot 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 tn. Okay, what is y1? That y at t1. Okay, and what is y at t1? That is L of x t1. You remember, I just say yk is what? Is equivalent to y of tk, that is equal to L of x tk. Suppose you have some value of this joint density. Now, instead of T1 or T8, suppose I give a shift plus C. Okay, that means that time what will be yk? It will be L of x tk plus C. Okay. Now, you remember, you understand that input this if in the earlier case when there was no such C added, the joint density will become actually function of the input statistics, because after all y1, y2, yn they are coming from input. Y1 is L of t1, L of x t1, y2 is L of x t2 dot dot dot. So, obviously, the joint density will depend on input statistics, that is input joint density. Now, if I want to find out the same joint density not at t1, but t1 plus c, tn plus t2 plus c dot dot tn plus c, it should depend on input joint statistics for what samples? X of t1 plus c, x of t2 plus c dot 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 x of tn plus c, but you see input is stationary, strict and stationary. So, whether you have the variables x of t1 dot 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 up to x of tn, or you have got the statistics will not change, because input is given to strict and stationary. What the LTI thing comes, because I said that if y1 is L of x t1, that is y of t1, y1 is y of t1, if y of t1 is L of x t1, then because of time invariance, y of t1 plus c is L of nothing but x of t1 plus c, that is y of then tk plus c, because of time invariance. So, when you have t1 plus c comma dot 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 tn plus c, the corresponding joint density again will depend on the joint density of x of t1 c comma dot 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 x of tn plus c, but because of strict and stationary of the input, that joint density will be, or that statistic will not be different from the earlier one when this constant shift c was not applied. Obviously, in the output case also two densities will be same and you get strict and stationarity. As an example of this linearity, you consider a differentiator, a system which takes x t and gives you first order derivative. It is obviously linear, because we know that derivation is linear, derivation is a linear operator. So, what is, so x prime t actually stands for your y t here. So, what is mu y t, also we can denote as mu x prime t, that is by your definition that will be like a L working on mu x t, and L working on this means what? You will have to differentiate it with respect to t. Then r x y t 1 comma t 2, which is also you can write as r x x prime t 1 comma t 2, that we have seen. L work on t 2 we have seen earlier of what? This input autocorrelation function, let us take it as a function of t 2 and then let the system work on it. But system work on it means then it will be differentiating it with respect to what? T 2. So, it will be del and just a couple of minutes, then I will be winding up. And the output or y y, which you can also denote as, that will be what? Obviously, you have to apply this R x x T 1 comma T 2 first with respect to say T 1. I mean say R x x T 1 comma T 2 will be passed into the system first as a function of say T 2, then the output will be passed through the system, but that time as a function of T 1 or vice versa, that you have seen. So, if you do that, that will obviously give rise to double derivative first with respect to T 1, then with respect to T 2. Order does not matter, it can be first del T and del T 1 and then del T 2 or vice versa. Okay. Stationarity, just 1 minute more. Suppose x t W S S, that means mu x t is constant, then mu x prime t, which is derivative of this, is 0. So, again it is stationary meanwise, you can easily have it verified here. This for the output also mean is constant. Then how about autocorrelation? That is, how about this R y y T 1 comma T 2. Now, here we have got R x x T 1 comma T 2 is a function of actually R x x T 1 minus T 2. T 1 minus T 2 equal to say tau. Okay, so, it is function of tau. So, here I know it is 1 minute. Here if you take this derivative del R x x T 1 minus T 2, okay, T 1 minus T 2 is tau, you differentiate with respect to T 2 first and T 1 first. I leave it as an exercise to you, you can easily verify these two things, R x x tau R x prime tau, you can easily verify, will be R x x tau first order derivative and R x prime tau will be second order derivative. Okay, so, that is all for today. Thank you very much.